I have these three kinematic equations that describe for me motion with constant acceleration. That's the caveat there, that I can only use these three equations to solve problems in which the acceleration is a constant. If I have constant acceleration, and then the acceleration changes to a different constant acceleration, then that's two separate problems. Only solving problems using these three equations shown here. In situations of constant acceleration, I can predict the velocity at some later time is the initial velocity plus the acceleration times t. I can predict the position at some future time as the initial position plus the initial velocity times time plus 1/2 the acceleration multiplied by t squared. And then I have this curious odd duck equation at the end here. V squared is equal to v naught squared plus 2a delta x. That equation is useful to me because sometimes in the problem statement, I don't know how much time has transpired for the motion. Since the third equation on my list does not require time, then it's useful for solving problems of that type. So problems of constant acceleration. It's a little bit limited, but we've discovered that there are lots of situations in our everyday world where the motion of things is either motion with constant acceleration or it's approximately constant acceleration. There's one very special case that we've already investigated. Early in our physics, pardon me, we studied uncertainty of motion. Not uncertainty of motion, uncertainty of measurement. Right? Uncertainty in all things, uncertainty in all of science. And we did so by dropping an object down the stairwell and performing an experiment related to the effect of gravity. Everyone knows that when an object is released near the surface of the Earth, it falls under the influence of gravity. And a moment of thought, you realize that as it falls, it goes faster and faster and faster. Perhaps this is an example of motion with constant acceleration. Indeed it is, and I've already revealed to you what that acceleration is. You may recall we did calculations using a number called g, 9.8 meters per second squared, the acceleration due to gravity. Now when we first used that number, it was a little bit mysterious, but now I understand that what it means is if I drop an object from rest and it falls under the influence of gravity, that it will add 9.8 meters per second to its speed as it falls. That is, after the first second of falling, it's now going 9.8 meters per second. And adding velocity and adding velocity and adding velocity as it goes. We can imagine the velocity under those cases, that would get quite large. But in fact, there's air resistance, which we don't consider, that slows things down as they fall. But for our model of the universe, our description, falling under the influence of gravity is motion with constant acceleration, and we call such problems free fall. Free fall because we're describing it considering only the influence of gravity and nothing else. It falls freely without any other impediment and moves under the influence of gravity. So what I'm going to do today is I'm going to solve a free fall problem. There's no new physics to this. It's just applying the physics that I already know to a situation that is interesting and useful. In all of my problem solving, I need a problem statement. I need a scenario. I need some sort of thing to investigate. So here's our problem for discussion here today. It's 1996, and Slim has just proposed to Peg. Slim is down here on the street level, and Peg is out the window. It's kind of a Romeo-Juliet situation. She's leaning out the window, and there's Slim, and he asks her if she will be his wife. She says yes, and he shows her the ring, all very excited. So he throws the ring upward to her with a velocity of 10 meters per second. And she's hanging out this window here, as shown, 4 meters above the point at which Slim releases the ring. The ring goes up, and the ring comes down. Under the influence of gravity, she catches the ring on the way down. And this is the problem that I would like to solve. But I haven't asked any question. Well, this is the way that it is when I do problems on the board. I'm going to figure out everything that I can. I'm going to fully explore the problem. There are a lot of questions here. You may realize by looking at it that it seems at first that I have very little information. I know that he throws the ring at 10 meters per second. I know that her outstretched hands are 4 meters above where he is. But I don't know any more than that. So at first looking at the problem, you might imagine that it can't be solved. Certainly it can. All I have to do is follow through with my problem-solving strategy, and everything is going to work out great. Along the way, I'm going to find that often in solving problems, I have to apply somewhat more sophisticated math techniques. That's okay. I don't have any problem with that. So I've drawn a picture here that represents the physical situation, but I must choose a coordinate system in which I'm going to solve the problem. The choice is completely arbitrary. I choose any way I like. But it turns out in this kind of a problem, in a free fall problem, I always make a very particular choice of coordinates. You don't have to. You can disagree with me. You can buck the system. You can do it your own way. But there are, I think, specific advantages to what I'm doing. I will choose where Slim releases the ring to be the initial position. That's where 0 is. And that's not surprising because I typically, in my problem solving, choose the initial position to be 0. That's how I like to do it. But I have chosen upward to be the positive direction. And you may think, well, it's kind of 50-50 on that. Because for part of the motion, the ring is traveling upward. For part of the motion, the ring is traveling downward. So I suppose you could choose either way. When I'm doing problems involving gravity, I always choose upward to be the positive direction. Always, always, always. And here's why. Consider this marker that I hold here and I throw it up in the air. When I throw it up in the air, it rises and falls under the influence of gravity. It goes upward, slowing as it rises, until it stops for an instant at the top of the motion, and then falls, speeding up as it falls back to my hand. Now, during that motion, the magnitude of the acceleration is 9.8 meters per second squared, but should I call it positive or should I call it negative? Observe, if I choose upward to be the positive direction, when an object is traveling upward and slowing down, the acceleration must be negative. Because for it to have a positive velocity and be slowing, I must subtract velocity in every second. And then it reaches the highest point in its motion where it stops for just an instant. And now it begins to fall. Now its velocity is negative because I have chosen upward to be the positive velocity, the positive direction. Now as it falls, its velocity is negative. So for it to speed up, which it does, I have to subtract velocity in every second. That is, the acceleration is negative on the way up and the acceleration is negative on the way down. In fact, the acceleration is negative 9.8 meters per second squared for the entire motion. It's not uncommon for honors physics students to think, well, the ring goes up and then it comes back down again, so I'm going to split the motion into two parts. The motion on the way up and the motion on the way down, I'm going to solve it as two problems. You don't have to do that. And you're going to see today, because I won't do that, I won't split the problem up. Because the acceleration is negative 9.8 meters per second squared the whole time. On the way up and on the way down, even at that very instant at the top, where it's at rest for a moment. The acceleration is negative 9.8 meters per second squared the whole time. So here's why I do this. When I solve problems of free fall, I will always choose upward to be the positive direction, and I do that because then I know that the acceleration is always negative 9.8 meters per second squared. Always, 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 always. By making that consistent choice, I reduce my chances of making a mistake. If I'm carefree about the choice, then every time I solve a problem, I have to think about what the acceleration should be, and then I stand a chance of making a mistake. By choosing upward as the positive direction, then acceleration is always negative 9.8 meters per second squared. Let's get busy solving this problem. That is, learning everything that we can about this situation. So I make my list: initial position, initial velocity, final velocity, time, and acceleration. And I need to fill out the list with the known quantities and put question marks for the unknown quantities. Do I know the initial position of the ring when Slim throws it? Absolutely, I do. I chose it. It's 0 meters. That's convenient and easy to do. Do I know the final position of the ring? In my description, she's going to catch it. And on my diagram, I've indicated that she is 4 meters above the release point. So do I know the final position of the ring? Sure, I do. It's explicitly given in the problem as 4 meters. Also, the initial velocity is given in the problem, 10 meters per second. I'm explicitly told that 10 meters per second is the initial velocity. It's positive because I've chosen upward to be the positive direction. Do I know the final velocity when the ring arrives at her hand? We're saying yes. You might be inclined to say 0 because you imagine that it hits her hand and she catches it and then there it is resting in her hand with 0 velocity. That's not correct. When I say the final velocity, I mean the velocity when it arrives. Does it have a velocity when it arrives in her hand? Yes, it does. When she catches it, she exerts an influence on it that is not free. We're describing free fall. So the motion is described from the instant it leaves Slim's hand to the instant it arrives at Peg's hand. And when it arrives, it has a velocity. Later on, there'll be problems where an object is dropped and it lands on the ground. And students will say the final velocity is 0. Really? Stand there and let it hit you on the head. Is its final velocity 0? No. It has a velocity when it arrives. And in this case, I don't know what that velocity is. Simply don't know what that velocity is. How much time does it take for the motion? I don't know. Unknown quantity. What is the acceleration? The acceleration is not explicitly stated in the problem, but it's a problem where an object moves freely under the influence of gravity. It is a free fall problem. And in free fall problems, the acceleration is going to be 9.8 meters per second squared. And because I have chosen upward to be the positive direction, then the acceleration is negative 9.8 meters per second squared. Now my list is complete. The units are all correct. The signs are all correct. I have all of my known quantities. I realize what the unknown quantities are. And now obviously a first step that I can take is to solve for the unknowns. But here, once again, I find myself in a situation where there's more than one way to proceed. And I'm going to proceed in the way that for me in this moment is educational. But there's more than one way to go about it, and that's perfectly fine. What I choose to do in this case is to first find the time that it takes from the moment the ring leaves Slim's hand to the moment Peg catches it. I want to find that time. And so I choose an equation. I know not to choose the third equation on my list, v squared is equal to v naught squared plus 2a delta x, because there's no time in that equation. I can't find time from it. I'm a little bit afraid of the second equation, so I go to the first. The final velocity is equal to the initial velocity plus the acceleration times time, but I don't know the final velocity. So if I choose v is equal to v naught plus at to solve the problem, I immediately realize it won't work. The only choice that I have is to find the time by using x is equal to x naught plus v0 times t plus 1/2 a t squared. Once I realize that the initial position is equal to 0, I also notice that I know everything in this equation except t. T is the only unknown, which algebraically means I can solve for t. Let me drop in the rest of the numbers. The final position is 4 meters, is equal to the initial velocity, which is 10, multiplied by t. Now, it's plus 1/2 at squared, but a is negative, 9.8 meters per second squared. You're going to get really used to this happening. Half of 9.8 is 4.9. So I'm going to write negative 4.9 times t squared. And hopefully, if you've been well trained in math, you realize what's happened. It is quadratic. In order to solve it, I'm going to have to use the quadratic formula. But before I do that, I like to rearrange my equation and put it in the quadratic form, so to speak. So I'm going to take this negative 4.9 t squared here, and I'm going to add it to the other side of the equation. That is 4.9 t squared minus 10t plus 4 is equal to 0. If you had not noticed that it was quadratic before, I think you can see it plainly now. Just as in math class, I'm given a quadratic equation as ax squared plus bx plus c. Here, I have 4.9 t squared minus 10t plus 4 is equal to 0. In order to solve it, I need to use the quadratic formula, or it's possible that you've realized how to use your fancy calculator to find the roots of a polynomial right off the bat. And if you can do that, feel free. It's not a math class. However, I think it'd be really super if every well-educated person knew the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a in order to find the roots. That's how I'm going to do it. So I'm going to find the time here by doing negative b. Well, the term that's in the b position here is negative 10. So negative that is 10 plus or minus the square root of b squared, which is 100, minus 4 times a, which is 4.9, times c, which is 4. Divided by twice a. Well, a is 4.9 and twice that is 9.8. That's the quadratic formula applied to this quadratic equation. Now, because of the plus or minus that appears in there, you know that there are going to be two answers to this. That is, there are going to be two roots. There are going to be two times. So you have to do a little bit of math there and work out what they are. One of the times is 1.59 seconds. That is one potential answer to the equation. But the other potential answer is 0.55 seconds. Sorry, not 0.49, pardon me, or 1.49. So my two possible roots here are 1.49 seconds and 0.55 seconds, which one's the right answer? It takes a little bit of reasoning to figure that out. But how I have described the problem in the problem statement is that the ring goes up and that peg catches it when it's on its way down again. The reason why the quadratic formula has two roots is because one of the roots is when the ring is on its way up and first passes the 4-meter mark. That is, it first passes her hands. And then the second time is when it's on its way back again. Whenever I use the quadratic formula in physics to solve a problem, I have to reason out which answer is the correct answer based on what I'm doing. Very often, that reasoning is easy to do because one root will be positive and the other one will be negative, and you can't have negative time, so it's easy to throw one of the roots away. In this case, it required a little bit more thought on my part. But now that I know the time that it takes the ring to go from Slim's hand to be caught by Peg at the top of the window, I can now calculate the other unknown on my list, which is the velocity of the ring when it arrives at Peg's hand. I'll use the first equation. V is equal to V0 plus AT. You'll note that I'm writing out my equations in standard form so that whoever looks at my solution knows what it is that I'm doing. The final velocity is equal to the initial velocity plus AT. So here, the final velocity, you give me a little help with the arithmetic, is the initial velocity, which is 10, minus 9.8 multiplied by the time, which is 1.49 seconds. What does that work out to? Someone, come on now. Negative 4.6. And Shiley, something's gone wrong. You've got a negative velocity. No, of course I got a negative velocity. A negative velocity makes physical sense here because the ring is on its way back down again. I've chosen upward to be the positive direction, so a negative velocity is completely appropriate here. A negative velocity is completely appropriate. So now I know the time it takes to go, and I know the velocity when it reaches Peg's hand. And so I filled out everything on the list. But as is very common with physics problems, there's more to know about the problem. There's more to know about the problem than just the things that are on the list. A very popular question to ask in free fall problems is, how high does the thing go? Because after Slim throws it, it passes Peg and flies way up here to the top of its motion. How high is that? That is, what is the maximum height that it reaches? Well, the thing about that maximum height is I don't know how long, I don't know how much time it takes to go to that maximum height. So calculating the maximum height seems to be a bit tricky because I don't know the time. But the maximum height has a characteristic that makes it possible for me to solve. At the maximum height, right here, at the maximum height, the velocity is equal to 0 meters per second. Just for an instant in time. At the maximum height, the final velocity is equal to 0, just for an instant in time. And that's what makes it possible for me to solve. Once again, I've gone off my list, so I should be cautious. But I'm going to use v squared is equal to v naught squared plus 2a delta x and solve for the case where the final velocity is equal to 0. What am I solving for? Delta x, the displacement upward to the maximum height. So if v squared is equal to 0, then negative v0 squared is equal to 2a delta x. And the delta x that I'm looking for is equal to negative v0 squared divided by 2a. Now you might look at this and say, well, now I've got a problem because you're going to get a negative answer. No, I'm not, because the acceleration is negative. The negative sign of the acceleration is going to cancel that negative sign that appears in the equation, so I get a physically reasonable answer. V naught squared, well, V naught is 10, so V naught squared is 100. I'll dismiss the negative sign because I know how that goes. 2 times 9.8. And what is my final value here? 490. You didn't divide 100 by a big number, 400. 5.1 meters. So I found the maximum height. As always, as promised, the solution of physics problems involves thinking. There's no getting around it. Thinking is required. It's not simply plugging things in and chugging. Today, I haven't demonstrated any new physics, but I've re-demonstrated the technique of problem solving in the context of motion solely under the influence of gravity, free fall.